All right, so a moment is a tendency of a force to cause rotation. Okay, so maybe I'll just write that up here. A moment is a tendency of a force to cause rotation. Okay, that is a moment. And then a special type of a moment is called a torque. It's actually, these are pretty much synonyms with each other, and yet they are used a little bit differently from each other in common usage. Okay, and I brought in a little, I use this to talk about a lot of these different things in statics. It's just a little piece of rubber here. I want to show you that basically this, if you imagine this being a member, you think about its axis being kind of its long ways, right? You think about this thing, the axis of it is going to be the part or the lengthwise direction of it, okay? And when you apply a torque to something, it's generally understood that you are talking about an action kind of like this, okay? You're kind of taking the thing and twisting it around its long axis, right? Whereas when you use the word moment, you generally mean that you're doing another kind of action, for instance, something like this, right? You're taking the thing and you're actually, you know, putting a tendency to rotate it, but it's on an axis that's not down its length, okay? Now, I'll say this. Mathematically, there's no difference between moments and torques, right? They're synonyms with each other for all intents and purposes. What I'm talking about here has more to do with how we commonly talk about things. Usually, if we're talking about an action that does this, we're talking about a torque. Whereas if we talk about an action that does something more like this, we usually talk about it as a moment. Okay? And there's a lot of things like that in life where you use a slightly different word depending on what kind of a context you're trying to describe. Okay? So here's the thing. How much tendency do we have to make something rotate? What's the mathematical expression for this? And so we'll take the most simple case first. Let's say that you have a rod that sticks up in the air, something like this, and you put a force on the rod in this direction, and it's a force of F, so that the line of action is pointing horizontally, and you know that it is a distance of d relative to the base. Okay? How much moment is induced about the base? I'll say the moment that F causes about the base, where this is the base down here, what would be a good expression of that, you think? F times D. Okay, and I'll say that that's a moment. Okay, now here's a couple of finer details that we need to take into consideration. The reason that this is the case is that the line of action of the force, okay, the force is acting like this, it's going along this line, the line of action of that force is already perpendicular to the direction that we're measuring the distance. In other words, if I was to kind of draw that a little more straight, we would say that this line where we're measuring that length or distance is perpendicular to the line of action of the force. And if you have that situation where you have a distance that's already perpendicular to the direction of the force, then all you need to do to figure out the tendency to cause rotation is just take the force times the distance. Okay? So that's what I'll say down here. Force is perpendicular to, I'll say maybe the line of action of the force. Is perpendicular to the direction where the distance is measured. Okay, so let's take another example. What if we have something where it's the same idea? There's a little beam that sticks up in the air like this one, but now instead of the force acting like it's shown there, what happens now if the force acts like this? And we know this distance of d. But now this force of F, let's say that we happen to know that that force of F acts at an angle relative to horizontal of theta. Now what? What can I do here? Okay, I could take f cosine of theta. What does that functionally do? Okay. Yeah, what it does is it allows me to take this force and basically split it into what? I can split that force into two components. The component that acts right here is what somebody said a second ago, f cosine of theta. What's this other component up here? That'll be f times the sine of theta. Okay. How much of a tendency to rotate does f sine of theta make on this rod? Like that component that points there that I've labeled f sine of theta. How much tendency to rotate does it make about the base? What do you say? 0, okay? If it's not contributing anything in terms of how it's going to rotate, I mean, the physical analogy of this is, let's say you've got this piece that's sticking up like this, okay? And you've got a force that comes in this way. You can split that into a force component that goes directly horizontal and another force component that pushes down directly vertical, right? And that force component that pushes down directly vertical, if I did it perfectly, it would have no tendency to cause this thing to rotate, whereas this one causes it to rotate. Would you agree with that? So that is correct. What someone said is you just take f cosine of theta, okay, and multiply by what? Okay, so that's how you would handle it if you have a force that doesn't get applied directly in a direction like that. Let's look at something else here. Another case. What happens if I have a rod that's maybe shaped like this? Okay, such that I have a force here that is applied to the rod, and maybe it goes straight down like this. And I happen to know that this body maybe has a dimension here of A and a dimension here of B. Okay, and again, we're going to look at about the base. What's the moment that's created about the base? Okay, back to our original definition. A moment is created by a force multiplied by a distance, but the force and the distance have to be perpendicular to one another. The line of action of the force and where you measure the distance are perpendicular to one another. So how do I handle it for this problem? Okay, I need to probably be more precise about what I mean by the base, right? What if I'm saying that that point right there is the base? Say that that's the point where I'm trying to find this moment about. How do I figure it out? This one's easy. Why is it just F times A? I mean, that's not how far away that point is from the point I'm finding the moment about, right? Should be the square root of A squared plus B squared. That's the distance, isn't it? Why is it this instead? Okay. So what you do here is you look at the line of action of the force. Okay, and imagine this line extending up and down forever. You say, I'm trying to find the moment about a particular point. What you do is you draw a line from this line of action to that point. How long is that line? A. Right? And that is how you figure out your moment about that point. Okay? What if I do a different one? What if I take this same idea and I change it just a little bit? Okay, I change it to where instead of the force acting like this, I leave my A and B the way they were. Instead of the force acting like that, I put my force on to where it acts like this. Now what moment is induced about the base? F times B. Okay? Now one of the things I have not been trying to be real careful about just yet is directionality. So let's look at between the one I did a second ago, the one up here, and the one that I just did. Okay? So between these two, do those tend to push this the same direction? In other words, if I applied one of them, would it topple over in the same direction as if I pushed it on it with the other one? Okay, I see a lot of heads going like this. Okay, a lot of heads saying no, they would not go the same direction. Does it matter? It kind of does, right? Because this, like what would happen if we did even another case that was just like these, but instead we actually put two forces on of F at the same time. How much moment is now created about the base? Okay. Now you might say the moment that's created is going to be equal to F times A plus F times B. And that's going to make a few of you cringe a little bit. And it should. Is this right? Okay. What if A equals B? If A equals B, would it even have a tendency to topple over? Okay, someone says no. And that's right. It would not topple over if A equal B under these situations. Why is that? One of the forces tends to try to make it rotate counterclockwise, and the other force tries to make it rotate clockwise. And if they have the same exact tendency to make the thing rotate counterclockwise as clockwise, they will balance each other out and come out to zero. Okay? So what we need to do with this situation, I'm going to put this as a note, we need to establish a positive direction. Okay? And there isn't just one way to do this. All right? There's not an absolutely correct way to do this. But it's important that you establish a direction that is positive, or else you won't know how to count each of the contributors. Right? You have to be consistent among all the things that are contributing to the tendency to rotate, or else it won't end up coming up with the right answer. So let's actually do this. For here, let's actually say, counterclockwise is positive. So if counterclockwise is positive, how should I change my expression there? Remember, this expression wasn't right. We have to fix it. What should I do? Okay. the F that's multiplied by A, does it tend to rotate the thing counterclockwise or clockwise? Okay. Counterclockwise or clockwise? Okay, it pushes down like this. If this was actually a physical thing that was resting on the ground, it would tend to make the thing want to do what? Fall over this way, which is counterclockwise. So I say, if I'm saying counterclockwise is positive, this one already has the correct sign. All right? Now let's look at this one. F pushing to the right, what direction does that make this thing want to topple? Clockwise, which is opposite of counterclockwise, which means this is the sign that is not correct, if this is my positive convention that I'm trying to use. Okay? So I change this like this, say F times A minus F times B, and that gives me my total moment. Okay? Sometimes what we do on these is we actually put a little symbol out in front and we say something like this. We say, you know, a little counterclockwise with a positive in the middle of it, something like this, right? That's not a bad thing to do to just make sure everyone is clear on what direction you are taking to be positive. All right? Shall we do a problem with numbers? Okay, let's say that you have a wrench that you're applying to a nut on a tire. Okay, so here's a tire. Here's a lug nut. I'll show a few of them on there to make it look more like a tire. Okay, let's say that the wrench that you put on your lug nut sticks up like this. Okay, it sticks up like this, and let's say that you begin to put a force on it, and let's say that the force that you apply, it comes down at an angle something like this. How much force do you want to put on it? All you got? Okay. All right. I'm about 200 pounds, you know, and if I'm really getting on this thing, maybe I'm bouncing on it, putting some dynamic load, maybe I can get that up to like 300 pounds. Okay, so let's say it's about 300 pounds. Okay, and let's say that I'm not being very careful about pushing straight down. And yet, I guess I am careful enough to measure the direction I am pushing. I don't know, but you know, let's say that that's what I'm doing. Okay, so let's say that I am careful to measure the direction that I am pushing, and instead of it being 90 degrees relative to horizontal, it is something like 80 degrees. All right, and the wrench, I didn't put it on there in kind of perfect position. So I also need to kind of establish where it is located. Let's say that it's at 20 degrees relative to horizontal. Okay, and that's up to the center line, which is also where the force is being applied. The wrench that I'm using has a handle that is how long? How long you want that handle? 16 inches, okay. Sounds good. And my question is, what is the moment induced around the lug nut by the wrench? And really, it's by the force we're applying to the wrench, right? Okay? How should we proceed? Okay, let's establish a positive direction. Let's say counterclockwise is positive. All right? So counterclockwise is positive. We've established a direction. What else should we do? I'll go ahead and establish a coordinate system there, a reference frame. That way our directions have an established meaning. What else do I need to do? Okay, we could draw a line of action of the 300-pound force. The 300-pound force has a line of action that goes like this, something like that. Does that help us? Okay. It might help us visualize what we're ultimately trying to get. What we're ultimately trying to get is basically the force of 300 pounds multiplied by a length that goes from here to here. If we could figure out that length right there, we'd be in good shape. But is that easy? I mean, it's doable, but it may not be easy, right? That's probably not the easiest way to solve this problem. What do you think an easier way might be to solve this problem? Okay.
Find the force in the y direction.
Okay, find the components of the force, all right? If we take this 300-pound force and say that is really the sum of a force that goes straight down, and the magnitude of that piece would be what? If we're going to take the sum of that force and then another force that goes to the side like this, the part that goes straight down is how much? £300 times I hear a lot of people saying the sine, okay? The sine of 80 degrees. Why is it the sine? Okay, notice where we're measuring that angle, it doesn't touch that component of the force. That means it's the opposite side. It does touch the line along which the other component runs, which means we're going to use the cosine on that side. So this piece is going to be 300 pounds times the cosine of 80 degrees. Okay, and what we're saying is that the red force there is really the sum of those two orange forces. Do you agree with that? That's what we do when we split something into components. Okay, does that help us? Yes, sir.
Could we rearrange the wrench to be 20 degrees and just add that to the 80? Or?
Okay. There are some things we could do there. I think the suggestion there is you could actually figure out components of force F so that you had one component that was parallel with the axis of the wrench and another component that was parallel with the axis or that was perpendicular to the axis of the wrench. Is that what you're kind of suggesting? I'll tell you what, I'll solve it that way next, all right? But we'll solve it this way first, and we'll do it this way. This method that I'm showing you here is basically you start by splitting your force into x and y components according to sort of horizontal and vertical, directions that aren't really, those directions aren't set up so that they are aligned in any way with the direction of the wrench. Okay, we can do it that way. If we do it that way, then we basically need to come up with two lengths as well. Let me ask you this. How far is it from the line of action of the 300-pound force to the point about which the moment is being calculated? Okay, this right here is going to be 16 inches times what? Okay, well, let me do it this way. This is a right triangle, right? So all of our right triangle rules that we use to split things into components and everything, they still apply. All right, so I have 16 inches times what? Yeah, the cosine of 20 degrees. Now, can I do something similar for the horizontal component? It has a line of action that acts right here. How far is that? Okay, 16 inches times the sine of 20 degrees. Okay, how does all that help me? When I calculate my moment with counterclockwise positive, I can add the effect of those two components of force, and the sum is going to be the overall tendency to rotate, which is the total moment. Okay, so what do I add? Okay, I've got to make sure I'm using a force value multiplied by a perpendicular length. Right, that's what I'm doing here. So which one do you want to start with? Okay, 300 pound sine of 80. That tends to rotate it in the counterclockwise direction, right? Okay, which means that I can leave it as a positive value. And I need to multiply it by what?
16 inches cosine 20.
Okay, so far so good. Then what? I'm not quite done, right? Because there's another component there that is the 300 pounds times the cosine of 80 degrees. Okay, and it tends to try to rotate it clockwise. So this should be minus 300 pounds times the cosine of 80 degrees times what? Times 16 inches times the sine of 20 degrees. All right, should I punch that in? See what we get? All right, we'll start over here. 300. I guess we got to get in the right mode first here. 300 times the sine of 80 times 16 times the cosine of 20 minus 300 times the cosine of 80 times 16 times the sine of 20. And that will give us 4156.92. What are those numbers? Okay, someone says inch pounds. Okay, and that kind of gives us a number that if this is, let's say this is a lug nut that's on there really, really tight, right? That gives us a number that gives us an idea of whether or not we might be putting enough torque on there to get it loose, right? Or those of you who've built things before, if you've worked on engines or transmissions or that kinds of thing, a lot of times there are specs about how much torque you're supposed to apply to your fasteners in order to assemble something properly, right? And it's given in units like inch pounds or something like this. What if I wanted it in foot pounds? Okay, right, there's 12 inches per foot, right? And so you would multiply by a foot over 12 inches in order to get it to feet, right? So you divide by 12, basically. 346.4 foot-pounds. Okay? Any questions? No questions? All right, let me do one last little thing, and then we'll go and work on some infrared LED stuff, some more hands-on fun kind of stuff. Okay, the last thing I want to do is let's generalize this just a little bit. Okay, let's say that we have a lever that we're applying a force to. Okay. So we have this. And let's say that we're applying a force on this lever, something like this. And actually, instead of showing the force like that, let me show it as a couple of components. Let's say I have a vertical component and a horizontal component. Okay, and let's say that relative to my x and y directions, which I'll put on here like this, relative to my x and y directions, let's say that I know how far it is to the horizontal direction. I'll call this A. Let's say I know how far it is in the vertical direction, and I'll call that B. All right. And let's say that this is fx and fy. Okay. How much moment am I going to create around point A? This is kind of generalized, right? How much moment am I going to create? Okay, I'll have Fy times what? Times A. A is this length right here. Then what? Minus Fx times B. Okay, what I want to show you here, this is something you've probably seen before, but I'll show it to you again. What I am basically doing is taking something that's called a cross product. Have you ever heard that term? Okay. Here is the fanciest way to kind of take a cross product. It's with the idea of a determinant. Okay, so a moment is really a determinant of I, j, k. What are these, I, j, and k? Those are called unit vectors. Okay, they basically are vectors of length 1 that point in the x, y, and z direction respectively. So I points in the x, j points in the y, and k points in the z. Okay, if you do this, and then in the next row, you put in components of a vector, which is basically a vector that points from the point you start up to the point where you apply the force. So let's call this the r vector. And let's say that A is basically equal to Rx and B is equal to Ry. Okay, so here we would basically put Rx, Ry, Rz. What do you think you put in the last row? Fx, Fy, Fz, and I really should have put just straight lines here because that's the symbol we use for a determinant. If I take the determinant of this, it gives me my moment. Let me show you what that looks like for this particular problem. For this particular problem, this is a 2D problem. So what happens here? We have still I, j, k. And what do we put in? We put in, okay, here we'll put in A, B, and 0. And what do we put in for F? For the Fx, Fy, and Fz. Okay, we'll put in Fx, Fy, and 0. Well, how do you take a determinant of a 3 by 3? Okay. This is the slickest way to take a determinant of a 3 by 3. you copy the first two columns and you paste them right here. And then what you do is you cross multiply. You multiply I times b times 0 and add j times 0 times fx and add to that k times a times fy. And then you subtract j times a times 0, I times 0 times fy, and k times b times fx. Okay? And it turns out for this that the only two of those multiplications that don't have a component or have a term of 0 in them are the one that comes right here. It starts to be hard to see that, so maybe I'll take that back off of there. And the other one goes like this. Okay? So what we need to do there is we take a positive, so m is going to be equal positive fy times a times k, and then a negative, because remember you subtract when you go along the green diagonals. You take minus fx times b times k. Okay, which basically just says that the moment is going to be equal to fy times a minus fx times b, all of this times k. What does that k mean? Okay, that is a unit vector that points what direction? In the z. So if this is my x and y coordinate system, that means that I've got a unit vector that's pointing straight out of the projector screen. All right? So what does that mean? It means it's three-dimensional. It means that we can represent moments with vectors so that the axis around which it wants to rotate, which would be that axis pointing out of the screen at A, right? This axis right here. The axis around which this thing is going to want to rotate is the axis that we describe that moment with. Okay? So that's kind of neat. And the value that is given here is the same that we would have predicted before we knew any of these steps that I just put on here. This is the idea of a cross product. How does it have relevance? Well, let's actually go back up to the problem we just solved and see if there's an easier way to solve it, knowing that you have a slick calculator. Okay? We'll see if that exists. All right, so let's pull out the calculator. And I want to show you that if you go to vector mode, let's see, we'll do that. We're going to go to vector mode. Actually, I need to do this first. Mode 8. Okay. First question it's asking there, I know it's not very clear, it says vector? Yeah, vector. I just said vector. Okay. No, it says vector. It wants you to enter data for one of your vectors. Okay. So which vector do you want to start with? Why don't we start with the vector of the handle of the wrench? Okay. What we're doing for the vector of the handle of the wrench is we're actually describing a vector that starts here and goes up here. How do I describe that vector in terms of components? Okay, I'll type 1. I want it to be a 3-element vector, so I'll select 1 there. All right. What are my components of that vector? The first one it's looking for is the x component. Okay, the x component is going to be 16 inches times the cosine of 20 degrees. So I'll put that in here, 16. Oh, and is it positive or negative? Okay. You look at the base of the vector being right at the point of the nut, and then the head of the vector extends to the left up to where the force is being applied. Okay. And so the direction of that vector matters. Let me kind of really emphasize this. This is the arrowhead right here. This is the vector that I'm finding. Okay, starts at the nut and points out to where the force is being applied. You always put it that way. And that means that you point to the left from where the vector begins to where the head of the vector ends. That means this is going to be a negative 16 times the cosine of 20. Okay? What about the y component of this vector? Positive 16 times the sine of 20. What about the z component of this vector? 0. Okay? This is the least intuitive step that we've gotten to now. We've entered the data for this. The next step is you hit AC. It feels very counterintuitive because it feels like you just cleared the stuff that you entered. I don't know why they made it that way, but that's the way they made it. We didn't clear it. It is still stored into vector A. All right? It's still in there. We just cleared it so that we could put another thing in here. The next thing we got to do is we got to hit Shift and the 5 key right here. It'll bring up a little menu. Okay? What we need to actually select out of this menu is option 2. It allows us to enter more data for another vector. And we're going to put this into vector B. Okay? And we're again going to do a 3-element vector into vector B. Okay? And what do you think we're going to put in for vector B? Okay? We need to put in the components of the force vector. So the x component of the force vector should be positive or negative? Positive 300 times the cosine of 80, because that's coming from this horizontal component right there. What about the y component? Okay, that's pointing downward here, so that'd be negative 300 times the sine of 80. And what about the z direction? 0? Okay. So we're ready to do now. We'll hit AC again. Now, we are going to take the cross product, and if your calculator is in the vector mode, which it is, you can tell that by the little symbol up here at the top, plus it gives us the options of putting in this data and everything. All that is only available in the vector mode. So what we're ready to do here is basically cross our A vector. To get that, we hit Shift 5, 3 times Shift 5, let's see, where is it? 4. What does it give us? Well, it gives us another vector, right? A vector whose only component is in what direction? The z direction, the k direction, right? It's in that last element. But the magnitude of that value is the value we just found a second ago, right? 4156.9. And if you want that to more precision, you can actually go and highlight that, and it'll give you all the precision you want. All right, so that's pretty slick, right? But you can make your calculator do that. The TI does the same thing, has the same functionality to it. All right, remembered that I told you that I was going to work a little bit different as well, where we were going to line up the force with the direction of the handle. Do you guys want to see that part? Yeah, let's do that part too. We may as well, right? We're here. We're having fun, right? Answer is yes, even if you're not, okay? That's a little pro tip. Just kidding. All right, so the other thing that we can do is we can take this same idea. I'll tell you what, I'll clean it up a little bit. This was our wrench stuck up this way, and we had this force of 300 pounds that was applied to it like this. Okay, and we had our x and y directions. We knew that this thing was 16 inches long. And the suggestion, oh, and we also knew this was 80 degrees. And I think the suggestion that we had was, what if we could figure out the component of this force that was applied to this handle perpendicularly and another component that was applied parallel to the direction of the handle? How would that be useful to us? How's that useful to us? Okay. If you can figure out just the component that's perpendicular to the handle, then you can just multiply it directly by the 16 inches and you're done. All right? Well, how do we get there, though? Okay. Well, I know that this is 20 degrees down here, right? This was 20 degrees. Can I bring that to bear on something that I'm doing up there on the top?
The one parallel would be 20 degrees.
Okay. So I think what we're saying here is that all of my values don't seem like they are, actually proportional here, but we're saying that this is 20 degrees, right? Because that's all one line, right? This is one line that extends from here down to here. So those would both be 20 degrees. If that's 20 degrees, then how far is it? I'll do it in a different color. How far is it from here to here? That's 60 degrees, right? Give myself a little room here. Okay, so if that's 60 degrees, then how do I figure out my two components? What is this component over here? Should it be 300 pounds times what? Sine of what? I don't think so. I'm not sure exactly what you're saying, but yeah?
In the two new forces you draw, aren't they 90 degrees apart?
Tell you what, let me try to draw this thing a little bit more proportionally. This would actually be coming down like this. That way that we will be more likely to get this answer correct and sort of verify it with how we drew it. This is 20 degrees. We're saying that this is 80 degrees relative to here. Okay, so this is 80 degrees. Okay, what we're trying to split this force into is a force that is parallel and another one that is perpendicular to the direction of the handle. And this right here is 20 degrees, which leaves this to be 60, which tells me that if I want the opposite component, right, which is going to be this one over here, I take 300 pounds times the sine of 60 degrees, which I think is the same conclusion I came to. Are you, maybe this is what you were saying. Maybe you were saying 30 degrees. Okay, which is fine. You could say 300 pounds times the cosine of 30 degrees. And that works too. All right. And so anyway, since this is 16 inches long, what's my moment? It'll be equal to 300 pounds times the sine of 60 degrees times what? And so what you were saying is true. You can go ahead and figure out what that perpendicular component is to the handle and just use that, because the parallel component to the handle doesn't create any tendency to rotate. All right.